Hello guys. In this lesson we will review the whole digital signal processing lesson using the solution of the example problems. Okay, so I split into two parts this example session. It's the first one, the continuous and discrete convolution. Examples. Okay, this is the first part. The second part is related to the Z transform. Okay. First we need to write the question 1 just like this one. Find the convolution yt xt star ht, where the xt input signal is the cosinus t and ht is equal to ut. Okay, with is equals to the what? The unit step function. Solution 1 can be given is just like that. The integral can be given by yt is equals to the what? The minus infinity to infinity value x tau times h t minus tau times d tau. Okay, and so we need to apply the whole this ht impulse response of this signal based on the what? The input signal. Okay, and so we can integrate all the solution in order to what? In order to get the total results. Okay, and then we can write that this integral yt is equal to the minus infinity to infinity value. Okay, and cosinus tau is the input one, and so u t minus tau d tau. Okay, and so these are the convolutional integral. Okay, and so this is equals to the what? To 1 for the tau smaller and equals than t, and we know that the ut is 0, t smaller than 0. Okay, and so this form simplifies that the yt is equal to 0 to t. Okay, because we have this condition tau is smaller than t, and then we can write the cos tau d tau. This is equals to the 1, and so we have a limit value in here just like this one, the 0, because the ut is the what? 0 if the t is smaller than 0. Okay, and so if we solve this equation just like this one, this is the integral form of the what? The sinus tau. Okay, and so we can write that the sinus t minus sinus 0, and then we can write that for this question is the yt is equals to the what? This is the 0 and this is the sin t. Okay, and so if you have a signal anything about the cosinus value, and then if we apply the impulse response of the unit step function, and then we will get the what? The sinus t. Okay, this is the first question. In the second question, question 2, compute the convolution of yt is equals to the xt star ht, where xt is equals to the sin t. Okay, and ht is equals to the what? The Dirac function t minus 2. Okay, being Dirac delta function. Okay, and so the solution of 2 can be built with the first of all, the integral of this term in the convolution form is equals to the yt minus infinity to infinity value x tau times ht tau d tau. Okay, and we know that the xt is equals to the sinus t and ht is equals to the Dirac t minus 2. Okay, but just remember that we have the t minus tau in here, and so this t minus tau is equals to the Dirac t minus tau minus 2. Okay, this is important. So we have this formula just like this one. Yt is equal to the minus infinity to infinity value sinus tau times Dirac function t minus tau minus 2 d tau. Okay, and so the importance of the Dirac function using in this equation, we just remove the integral term in here because this function returns to the t minus tau minus 2 is equals to the 0, and then we will get the 1 value. Okay, this is the instant value, and so we don't need to compute the whole integral, just like this form should be calculated in here. Okay, and after that we can say that if we have this condition t minus tau minus 2 is equals to the 0, or tau value is equals to the t minus 2. Okay, and so this integral yields us in here to yt sinus, but the tau must be equals to the t minus 2. Okay, this is the solution of the Dirac delta function applied on the any function. Okay, and so we need to compute, or we don't need to compute the total integral, just compute to the tau value at this case. Okay, this is important. So in the third question, we should solve the system or system dynamic equation. For example, take the RC circuit, like we can draw the RC circuit in here just like this one. We have the one resistance value, one capacitance value, R and C can be given in here. Okay, and so we can apply the V in, and we can take the output values of the V out. Okay, and apply to this signal to the unit step, and then find the V out solution for convolution integral. Okay, the solution 3 can be given in here. Firstly, if you have this kind of system, we need to step by step solve this equation. Okay, and so using the time domain information, firstly V in must be equals to the I times R is the voltage values of the resistance, and also we have the V out with the I must be equals to what? The capacitance value times dV out divided by dt. Okay? And after that, we can write this equation. V in must be equals to what? The RC dV out dt plus V out. This is the first order equation for A. Okay? And after that, we should continue with what? Taking the LP like V in is the unit step, which means that we have the 1 divided by S in here, just like this one, because we have the Laplace transformation of the what? The unit step signal, 1 divided by S. Okay? And so we can write that the 1 divided by S must be equals to the what? The RC S V out S, because we have the differentiation operation in here, just like this one. And so V out S must be written in here. Or in another way, the V out S times RCS plus 1 must be equals to the what? The 1 divided by S. Okay? And so if we reorganize the whole equation in here, and then V out S must be equals to what? The 1 divided by S RCS plus 1. Okay? In the Laplace transformation, we can split to what? To this term into the two parts, right? In order to solve easily, just like this one. AS plus B RCS plus 1. Okay? And so the solution coming from the what? The V out T is equals to the what? The 1 minus E minus T divided by RC. Okay? This is the R solution for the what? The V out equation in here. Okay? RC. But this is found using the what? The R Laplace transformation perspective. Okay? But we need to, this is the correction term or the performance indication for the what? For the solution. We need to reach this value, but we need to use the what? The convolution theorem to reach this application. And so what is the solution? Instead, the taking inverse LP gives us for the homogeneous solution or the impulse response of this system can be calculated with what? The HS is equals to the what? 1 divided by RCS plus 1. Okay? We do not apply the 1 divided by S in here. We just use the 0 value in here, and then we can take the what? The general impulse response function to what? To these RC circuits. Okay? And so this is simplified with the what? The 1 divided by RC S plus 1 divided by RC, and it yields us to what? The HT is equals to what? The 1 divided by RC times exponential term minus RC. Okay? This is the R general depiction or the representation of the R circuit in here. Okay? This is the impulse response to be used in the convolutional integral. Okay? And after that, the YT, the convolution XT star HT can be calculated with the what? With the integral term of the what? The infinity to infinity value U tau. This is the what? This is the input value, unit step function. And we can write the 1 divided by RC exponential term minus, in this case we have the T minus tau in here, just remember that, and we can take the D tau in here. Okay? And so if this is the unit step, and so we can write that the 0 to T value is the R region in here, 0 to T, and so we have RC times E minus T tau divided by RC times D tau. Okay, this is the R integral to be solved in the what? In the convolution integral. Okay, and so in the 5 we should write the what? The yt can be simplified as the 1 RC. This is the constant term E over T divided by RC because it's independent from the what? The tau value 0 to T, and so E tau RC D tau. Okay, and so if we solve this equation, and then the yt is equals to y1 divided by RC exponential T RC, and 0 to T is the integral solution RC times E tau RC. Okay, the integral yields these calculations. Okay, and then the yt again the calculated as the 1 RC E T RC times RC, this is the constant term, and we have the parenthesis term, the T RC is the first term, minus 1 because we have the 0 value exponential over 0 which is equal to the 1. Okay, and so and this is also equals to the what? The E minus T RC, because this RC removes the whole the terms in here just like this one, and also we have the T RC minus 1. Okay, and then what? The final yt can be written as to what? Yt is equals to the what? These terms multiplication with these terms yields us the 0 value at the over part, and so we have the 1 value minus exponential minus T RC is the R solution in the what? In the convolutional integral. Okay, and so the Laplace transform is also given this calculation in here, and then the R convolutional integral yields us this value. Okay, and this is true, and so in each step we should take the what? The firstly we need to design the time domain information, the dynamic equation of this term, and then we need to take the Laplace transformation to what? To taking the what? The impulse response of this form, and then we should apply the convolutional integral with terms of this one. Ut yields us to what? The 1 if the t is bigger than 1, otherwise the 0, and so we have the lower limit as equals to what? The 0, and the other one is the t because it's dependent of the t in here. And then we can solve this equation, and then we will continue or the reach to the what? The yt solution with the based on the what? The convolutional integral. Okay, okay, in the question 4, assume that you have a system like x dot plus 5x is equals to the ft. Okay, these are dynamic equation. Okay, for a given any system with the terms of the what? The ft is equals to 5 times ut, unit impulse response. Okay, and then solve this output using the what? The convolutional integral. Okay, the solution for can be given in the what? We must firstly find the impulse response for this system because we have the dynamic equation here just like this one, and then we need to apply the 5 times ut as a ft to this system in order to take the output results. Okay, and so Just like the previous example, we need to build a step-by-step solution in here. Okay, in order to find out this system, the impulse response of this system, we need to apply the ft is equals to what, the Dirac function in here. Then the x dot plus 5x is equals to what, the Dirac function. Okay, and so taking the LP for x0 is equal 0, and then we can take the xs plus 5xs, which is equals to the 1, just like in the previous example. Remember that we use the unit step in here, but in the Laplace transformation, Dirac function yields us equals to the 1. Okay, and so the xs is the what, the 1 divided by s 5. Okay, and so the taking the inverse Laplace transformation yields us to what, the impulse response of this system. Okay, L over minus 1 divided by s plus 5, which is equals to what, the e over minus 5t times ut. Okay, these are the what, the impulse response, the general depiction of the what, the system, in terms of the what, in terms of the time domain. Okay, and so in the second place, we need to take the convolution integral like ft is equals to 5 ut in here, and so the yt is equals to the what, the ft is the input value, star operation ht is yield us to what, the minus infinity to infinity value f tau times ht minus tau d tau. Okay, where the f tau is equals to what, the 5 u tau, and ht minus tau is equals to the what, the e minus 5 t minus tau times u t tau. Okay, these are two solutions, and then the integral becomes to the what, the yt is equals to 0 due to the unit step function and the t in here, and 5 times exponential minus 5 t tau d tau. Okay, and so this yields us to what, the 5 is the constant term and the t is also independent from the tau value in here, and so e minus 5t times integral 0 to t value e minus 5 d tau. Okay, and then we can solve this equation based on what, the yt minus 5 times e minus 5t times 0 to t e 5 times tau divided by 5. This is the integral term on these terms, and so exponential term minus 5t exponential 5 times t minus 1. Okay, and so this is yield us to what, the yt is equals to the what, the 1, because this terms removes the other one, and exponential minus 5t. Okay, and so our solution should be equals to this one. Okay, for the what, for the 5 unit step impulse response to the given of the system. Okay, So in the next place, we need to continue with what the section 2 in here, just like this one, the Z transform and the difference equation. Just now, we need to utilize the solution of the discrete domain based on the Z transform instead of the Laplace transformation. Okay. Okay. Question 5 is related to the Z transform. Okay. Assume that we have a system like x dot plus ax, which is equal to u, and solve it using backward difference equation. In Z transform. Okay. So the solution can be written like, firstly, the applying backward notation, we get the xk minus xk minus 1 divided by dt must be equals to the what? This is the solution of this term. X dot is equals to the minus ax plus u, and we can write that the a minus a x k minus 1 in the backward notation, because we have the past value in here. This is the future value. Okay. And so plus u k minus 1. Okay. So the xk minus xk minus 1 is equals to the what? The dt times minus a x k minus 1 plus u k minus 1. Okay. And then we will reach to the what? The xk is equals to the what? The xk minus 1 times 1 minus dt times a plus u k minus 1 dt, right? This is our solution for the system. Okay. These are the general difference equation for this implementation of the continuous equation. Okay. So if we have this information, and then we can apply Z transform in here to the discrete equation, and then we get the xz, this is the k term in here, just like this one, and xz times z over minus 1, because we have the k minus 1 in here, just like this one. Okay. And 1 minus dt times a plus z over minus 1, because we have the uk minus 1 in here, uz times dt. Okay. And so if we collect the whole the terms into the what? The xz value in here, minus 1 minus z over minus 1 dt times a in here, just like this one, z over minus 1 uz times dt. And so we have the pulse transfer function in here, xz uz is equals to the what? The z over minus 1 dt plus 1 minus z over minus 1 dta. Okay. These are the general solution or the z transform of the R equation. Okay. We can solve it using the time domain information or the discrete equation. So in the next question we will solve more complex equation, the question 6. Okay, consider that the MCK mass spring damper system with the form of the M x dot plus C x dot plus K x is equals to U, with the parameters of the M equals 1, C equals 3, K equals 2. Okay, and solve this equation using centered difference equation. Okay, in Z transform. This is much more complex solution because we have the second order system in here. Okay, firstly we need to talk about the centered difference equation. Equation yields us to what? Firstly, x dot can be expanded in terms of the xk plus 1 minus 2 times xk plus xk minus 1 divided by with the dt square sampling period. Okay, and x dot is equals to the xk plus 1 minus xk minus 1 divided by dt. Okay, and x is also considered as the k terms in the centered difference equation. Just remember that in these operations are most important part to to convert your continuous system into the discrete one. Just remember that if we write this term as the k minus 1, and then we cannot easily solve these equations. Okay, so in that domain we should this formation just like this one. Okay, and so x dot should be replaced with with this term, x dot with this term, x with these terms. Okay, and so if you write the equation xk plus 1 minus 2 xk plus xk minus 1 divided by dt square, because m is equals to the 1. Okay, and also plus 3 is the c coefficients in here, xk plus 1 minus xk minus 1 divided by dt. Okay, and also plus 2 xk is equals to the uk. Okay, and so this is the R equation for the discrete notations. Okay, so how we can reorganize whole the equation using these informations? Reorganizing discrete equation yields us to what? We must firstly collect the whole the terms related to xk plus 1, which is equals to the 1 divided by dt square plus 3 2 dt plus xk times minus 2 dt square plus 2 and plus xk minus 1 times 1 dt square plus, no, it's not plus, minus 3 2 dt. Okay, and uk must be given in this case. Okay, for the simplicity we can assign this is the f1, this is the f2, and this is the f3, and we can write this equation just like this one, xk plus 1 times f1 plus xk times f2 plus xk minus 1 f3 is equals to what? The uk. Okay, and so in order to build up our difference equation, we just take the xk plus 1 at the left hand side must be equals to the what? To the other part. Okay, and so this part and this part should be moved to the what? To the right hand side. Okay, and so xk times minus f2, because this is goes to the right hand side, divided by f1 because the xk plus 1 multiplication with the f1 is here. Okay, and plus xk minus 1 times minus f3 f1 plus uk is just simply divided by with what? The f1. For the simplicity value, we can assign another term, g1, g2, and g3. Okay, and so we can say that the xk plus 1 must be equals to what? The xk times g1 plus xk minus 1 g2 plus uk times g3. Okay, these are the difference equation which is expanded with the what? With the centered difference equations. Okay, so in the second place we should apply the z transform. To this equation, and then we have the z times x z, because we have the k plus 1 in this, in here, related to x, which means that this yields us the z over 1. Okay, and so x z times g1, because this is the k in this, and so z over minus 1 times x z times g2 plus u z times g3. Okay, and so we collect the whole the x z terms at the left hand side, z minus g1 minus z over minus 1 g2, which is equal to what? The uz times g3. Okay, and so our pulse transfer function can be written as the what? The uz xz divided by uz is equals to the what? The g3 divided by z minus g1 minus z over minus 1 g2. Okay, these are the pulse transfer function, but we can write this equation as the what? As in this form, xz us, which is equals to the what? The g3 z z square minus g1 z minus g2. In this case, we can multiply this equation with the what? With the z and divide by z. The mathematically, it cannot change the anything in the equation. Okay, or we can multiply the r equation is the what? The z over minus 1 z over minus 1, just like this one. X z uz is equals to the what? The g3 times z over minus 1, and 1 minus g1 z over minus 1 g2 z over minus 2. Okay. And so these two equations are identical, but with one big difference, which means that in this case we only contained in the water k minus 2 in this should be given in here, which means that if we take a measurement from the system and if we have only past values of the R measurement, we should use this form. But the other term is the xk plus 2, which is given in here just like this one, and so which means that we need to have the future values of this equation because we have the z square form in here just like this one. Okay, this is important because in the real-time application we may use either this form or this form. It's depending on the implementation of your system. Okay, and so another term is that if we have this equation in here, we can check the stability of the system. Like what? If we have this equation xz uz is equals to the g3z, this is zeros, z square minus g1 z minus g2, and so in order to take the stability values of this term, we should assign the z square g1 z minus g2 should be equalized to 0, and the z root 1 and z root 2 must be contained with the with the 1 value, or in another term minus 1 z1 z2 condition should be satisfied for the for the stability rule. Okay, we can say that this system is stable if this condition is satisfied. Okay, so this is the second order system implementation of the R equation, and so the R problem solving session is ended right now. Okay.